Good morning everybody. Myself Ritik Maiti, research scholar from Department of Mechanical Engineering, IIT Kharagpur. So this is a tutorial class on adiabatic two-phase flow and flow boiling in microchannel. This class has two sections. In the first section, Mr. Alex Koshi will discuss some numerical problems related to phase flow, and it is based on the classes which have been conducted, and this is a part of assessment of this course. So he will discuss one problem related to nomenclature type and one problem related to calculation of pressure drop in a typical two-phase flow when it flow through a conduit. And in the second section, mainly content with the computational fluid dynamics in two-phase flow, and this is a not part of this assessment of this course. In this part, Mr. Minmay Dhar will discuss in CFD and CFD in two-phase flow. He will also discuss in briefly the simulation of two-phase flow with the help of open source like JRIS. And then Mr. Abir Chakraborty will also discuss simulation of two-phase flow to find out the flow pattern and pressure drop with the help of commercially used software package like COMSOL. So now I am just hand over this class to Mr. Alex Koshi. Thank you.
Hello everyone, I am Alex Koshi. I am the TA for the course Adiabatic Two-Phase Flow and Flow Boiling in Microchannel. So in this tutorial I am going to present a few numerical problems that are related to multi-phase flow. So the first problem, as Mr. Ritik Maiti has already given an introduction about what my session will be. The first problem is a nomenclature related problem, and the second one is a typical multi-phase flow problem that deals with the pressure drop calculation that is involved when a two-phase mixture flow through a microchannel. So I am going straight to first problem. So I will read it once. Derive the relations to express X, the mass quality, in terms of volumetric quality beta and phase densities rho L and rho G. Mass quality of air in the system, suppose if it is an air water system, the mass quality air in the system can be represented as WA by WL plus WA, where A is the WA is the mass flow rate of air and WL is the mass flow rate of liquid, and it can be written as QA rho A by QA rho A plus QL rho L. Okay, where QA and QL are the volumetric flow rates of air and liquid phase, and rho A and rho L are the phase densities. In the similar way, we can write 1 minus X, that is the mass quality of liquid phase, as QL rho L by QA rho A plus QL rho L. All right. Yeah. Now this is equation 1 and this is equation 2. So we are dividing 1 by 2. Therefore, we will get an equation like X by 1 minus X is equal to QA rho A by QL rho L. Now I am dividing both the numerator and denominator of this equation, of this term, with QA plus QL. Okay. Now if we see, we are having QA divided by QA plus QL term here in the numerator, and QL by QA plus QL term here in the denominator, and this is nothing other than beta, that is the volumetric ratio, volumetric flow ratio at the inlet, and here QL by QA plus QL is 1 minus beta. Okay. Now I am simplifying that equation by cross multiplication. Okay. Now after further simplification, we will get the value of X as we can express X as Thus we have expressed X, the mass quality, in terms of beta and phase densities. Now we go to the second part, that is a slip ratio K. It need to be expressed as a function of alpha and beta only. As we know, K is the ratio of in situ velocities of gas phase divided by in situ velocity of liquid phase, and this can be written as Qg by Ag divided by Ql by Al, where Qg and Ql are the volumetric flow rates of gas phase and liquid phase, and Ag and Al, suppose we are having a conduit, we are having an annular flow. This is the air region, this is the gas region, and this is the liquid region. The area, the fraction of area, the area obtained by the gas region is termed as Ag, and the area obtained by the liquid region is termed as Al. Thus Ag can be written as A into alpha, and Al can be written as A into 1 minus alpha, and this A and this A will be cancelled out. Thus we get K as Qg by alpha divided by Ql by 1 minus alpha, and I divide both numerator and denominator with Qg plus Ql. Alright, and now if we see, this term is, as we got in the first problem, this term can be written as beta, and this term can be written as 1 minus beta. Therefore we got K, the slip ratio, as beta by alpha divided by 1 minus beta by 1 minus alpha, and it can be further simplified to beta by 1 minus beta into 1 minus alpha by alpha. So now we go to the second problem. I will read the problem once. Air and water flow through a horizontal conduit of diameter 400 micrometer and length 4 centimeter. Assuming homogeneous isothermal flow at room temperature, calculate the frictional pressure drop across the conduit. So we have been provided with certain data that are the superficial velocities of liquid and gas phase, that is 60 millimeter per second and 10 millimeter per second, and we have been provided with the phase densities as well as phase viscosities. Now before going to the frictional pressure drop estimation, I would like to tell you something. The pressure drop across a conduit can be categorized into 3 components. First one is gravitational pressure drop, and second one is frictional pressure drop, and the third one is accelerational pressure drop. So here in this case we are neglecting gravitational pressure drop because first of all it's a horizontal conduit, and secondly the amount of liquid that is contained in the conduit is very small, so we can neglect the gravitational pressure drop here, and we will be calculating the frictional pressure drop. And talking about the accelerational pressure drop, we can neglect the accelerational pressure drop if there is no phase change as well as if there is no compressibility effects involved in the system. So suppose if the relative change in specific volume across the specific volume happening across the system is greater than 5%, we have to consider accelerational pressure drop. If it is less than 5%, we will neglect accelerational pressure drop. So for the time being I am neglecting accelerational pressure drop. I am assuming that there is no accelerational pressure drop that is involved because mainly there is no heating of conduit occurring, there is no phase change occurring. So I am taking only frictional pressure drop as of now, and at the end I will cross check whether my assumption of neglecting acceleration pressure drop is right or wrong. So now going to the frictional pressure gradient calculation, it can be calculated using Darcy-Weisbach equation, and the equation is shown in the screen right now. While looking in the screen, we can find out that there are plenty of unknowns involved here. One is FTP, one is GTP, and one is rho TP. and dH is a hydraulic diameter. Here, as it is a circular channel, we can take the hydraulic diameter as the diameter of the conduit. And GTP, we need to find out the GTP, that is the total mass flux of the two-phase mixture across the conduit. It is the sum of GL and GG, that can be written as rho L JL plus rho G JG, where JG and JL are the superficial velocities, phase velocities, and rho L and rho G are the phase densities. We know all these values have been given, and we got the value of GTP as 60.01225 kilogram per meter square second. I am writing the value straight away because I am having a time restriction. That's why I am not doing the calculation. I have already calculated it. And now rho TP, it can be found out as rho G into alpha plus rho L into 1 minus alpha. Alpha is the in situ volume fraction. As we are assuming it is a homogeneous flow model, we can take alpha as beta, that is the inlet volumetric fraction, and it can be written as Qg divided by Ql plus Qg, where Q, G and QL are the phase volumetric flow rates. It can be written as A into Jg by A into JL plus JG, where J, G, Jg and JL are the superficial velocities of phases. Thus we can cancel out A and A from numerator and denominator. Thus it becomes Jg by JL plus Jg. We got the values of Jg and JL. Thus we got the value of alpha as 0.143 and 1 minus alpha as 0.857. And we substitute the value of alpha and 1 minus alpha here. We got the value of rho TP as 857.175 kilogram per meter cube. So now we got GTP, we got rho TP. If we look at the equation, we see that only one unknown is remaining, that is FTP. So for the estimation of FTP, where F is the fanning friction factor of two-phase mixture. Okay. Suppose it was a single phase flow case, what we would have done, we would have found out the Reynolds number RE associated with the process, and if RE comes below 2100, that is a laminar regime, we would have taken 16 by NRE as, 16 by RE as the fanning friction factor value, and if RE is greater than 2100, that is a turbulent regime, we would have either took the value of F as a constant, that is 0.005, or we would have used the correlation 0.079 RE raised to minus 0.25, or we would have found the value of RE from Modi's plot. Here I have already found out the value of RE, and the value of RE is 24. Value of RETP, two-phase Reynolds number, is 24, and that comes in the laminar regime. But we cannot use this equation because this equation does not take into account the wall interactions, the wall effects that are involved in the flow process. So we are not taking this equation. Instead of that, we are going for another equation, which is termed as the Churchill equation, and this Churchill equation is applicable only for an x value that ranges from 0 to 0.25. X value is the mass fraction value, mass quality. Okay, so we need to calculate the mass quality first of all, whether to see if it comes in this range 0 to 0.25. So mass quality X can be found out as Wg by W L plus Wg. Here we are cancelling out the A value, thus all the remaining value we have already, it's already given. Jg value is given, rho G, rho L, JL all are given. Thus we got the value of X as 2.04 into 10 raised to minus 4. and if we see this value, it comes in the range 0.25 and 0. So we can use Churchill equation for our calculation for the estimation of FTP. If we look at the equation, there are plenty of unknowns here. There is an A, there is a B, there is RATP that we have already found out, and there is a C1. For circular tubes, the value of C1 is given as 8. And for RATP estimation, we know that RATP is equal to D into GTP by mu TP. We know the value of D, we know the value of GTP. We need to find out the value of mu TP, and mu TP can be found out using equation 3. Here if we see, we have got the values of mu G, we have got the values of mu L, and we got the value of X. So substituting all these values, we will get the value of mu TP, and if we substitute the value of mu TP here, we will get the value of RATP as 24. Okay, and this comes in the laminar range, and we substitute the value of RATP here. We need to find out A and B value, and to find out A and B value, we got equations that is given under equation 4, and B value we can find out straight from the RE value that we have got, and A value, for that we need to find out 1 by root CT, and for circular tubes the value of 1 by root CT is given as 2.457, and we know the value of RE. Here there is a term that includes a component known as epsilon D, that is the roughness factor involved in the process. Here we are assuming that it is a smooth conduit, so we take the value of epsilon D as 0. Thus the whole term 0.27 epsilon D by D cancel out. So we know the value of RE, we know the value of 1 by root CT. Thus we got the value of A and B as okay. And now I substituted all the values here, A, B, RATP I have got. I substituted all the values, and I got the value of fanning friction factor FTP as 2.67, and I have substituted the value of fanning friction factor here in Darcy-Weisbach equation, and I got the pressure gradient dP by dz FTP as 56090.79 Pascal per meter. And now we need to find out the pressure drop value from the pressure gradient value. It can be found out using this equation, using integration across the conduit length. And this is equal to minus dP by dz FTP into L. L we know it is, the value of L is 4 centimeter, that is 0.04 meter, and by doing the calculation we get the value of delta P pressure drop as 2243.63 Pascal. Now we got the value of pressure drop using homogeneous flow model. Now initially I have told you that we have neglected the acceleration pressure drop value, so we need to cross check whether our assumption to neglect acceleration pressure drop value was right or wrong. So in order to find out that, I assume that the inlet pressure is Pi and the inlet specific volume is Vi, and the inlet temperature is the room temperature, that is 298 Kelvin. The outlet temperature is the same because it's an isothermal process, it is 298 Kelvin. Outlet pressure, it is the atmospheric pressure, that is 101325 Pascal. Outlet volume we need to calculate. We need to calculate V0, we need to calculate Vi, and we need to check whether this relative variation is greater than 5% or less than 5%. So we have calculated the value of P, Vi and V0 from ideal gas law. The value of R we know, it is 8.314 joule per Kelvin mole. And now substituting all the values, I got the value of Vi as 0.0239 meter cube. I got the value of V0 as 0.02445, and I forgot to mention I got the value of PI by adding the outlet pressure plus the pressure drop, and the value of PI is 103,568.63 Pascal. Now we have the VI value, we have the V0 value. We need to find out the relative change in volume, specific volume, delta V by VI. And I got it near 2.3%. That's obviously less than 5%. Thus we are neglecting any kind of compressible effects, and thus we assume that our assumption to neglect the accelerational pressure drop was right. And now we have found out the pressure drop using homogeneous flow model, and I am repeating the same method, means repeating the same process, that is finding out the pressure drop across the conduit using another method, that is the method that uses Martinelli parameter. This is approach 2. Here Martinelli parameter chi square is phi g square by phi l square, where phi g and phi l are two phase multipliers, and that can be written as minus dp by dz f l and g, where this term is the pressure drop that is involved when the liquid flows alone through the conduit at a mass flow rate at a mass flux of GL, and this happens when gas flow alone through the conduit at a mass flux of GG. And we use the same procedure, that is the Darcy-Weisbach equation plus the FTP estimation using Churchill equation. We use the same thing for the calculation of single phase pressure drops, pressure gradients, and we got the single phase pressure gradient values as we substitute these values here, and we got the value of chi square as 302.95. okay, and now we have a correlation known as Chisom's correlation. There we substitute the value of chi square and chi, and we get the value of phi l square, that is the value of two phase multiplier. And here also we got an unknown, that is C. For viscous cases, that is the case that we are encountering now, because the Reynolds number involved when liquid flows alone through the pipe as well as conduit, as well as the gas flows alone through the conduit, both comes under the laminar regime. So we take viscous case here, we take the value of C as 5, and we substitute the values in this equation. And we got the value of phi l square as 1.291. okay, and now what is phi l square? Phi l square is minus dp by dz ftp, that is the frictional pressure drop involved when two phase mixture flows through the conduit, by frictional pressure drop involved when liquid phase flow along through the conduit at a mass flux GL. And here we need to find out this value. This is our pressure drop, pressure gradient, and this value we already know, we already found it out, and the value was found out to be 48060. We substitute the value here and we multiply 48030, that is this value into this value, and we got the two phase frictional pressure drop value as okay, and from this value we got the pressure drop value as we found out earlier as 2481.82 Pascal. And this is the pressure drop value that is calculated using Chisom's correlation. We found out earlier that the value of pressure drop calculated using homogeneous method was if we see, we can find out a small difference between these two values. These two values were obtained from two different methods, and this difference is basically due to the fact that in Chisom's correlation it is assumed that there is no interaction between the phases at the interface, and in homogeneous flow model it is assumed that complete interaction occurs at the phase interface. Complete interaction occurs between the phase at the phase interface. Okay, and these two are two extremes. I will show you a graph. This has been taken from a literature, and the top curve, it denotes the phi L square, that is two phase multiplier values for Chisom's correlation method, and the bottom curve denotes the two phase multiplier value obtained from homogeneous flow method. And in this case, at low mass quality values, we can see a deviation, and this deviation is due to the fact that I have explained earlier. And in reality, the pressure drop value will be somewhere in between these two values. So before winding up, I will just summarize what all I have done in the second problem. I have adopted two methods in order to calculate the pressure drop of two-phase flow through a conduit, and first method is homogeneous flow model method, and second one is Chisom's correlation method. And in the homogeneous flow model method, I have found out the values of GTP, rho TP, FTP, where FTP value is found out using Churchill equation, and I have substituted the values in Darcy-Weisbach equation to get the value of two-phase pressure gradient and thus the two-phase pressure drop. And then I have cross-checked whether the assumption to cancel out acceleration pressure drop was right or wrong by checking if the relative change in specific volume was less than 5%. And in Chisom's correlation method, I have found out the value of Martinelli parameter using values of single phase, that is water and air pressure gradient, and from the value of Martinelli parameter using Chisom's correlation, I have found out the value of two-phase multiplier phi L square, and from there from the values of two-phase multiplier as well as liquid phase pressure drop, I have found out the two-phase pressure gradient and pressure drop. That's all from me. Now Mr. Mrunmay will be explaining the basics of CFD analysis of two-phase flow using JERIS software. Thank you.